Linear Algebra Part 4. Inverse of a matrix, definition and properties. The inverse of a square matrix A, denoted by A minus 1, is the matrix that satisfies the following condition, which is A multiplied by A minus 1, or the multiplication of a matrix with its inverse, should be equal to the multiplication of the inverse with the matrix itself, so you can flip the order, and it should always give us I, which is the identity matrix having the same size, the same number of rows and columns as the original matrix, and which has, I'm talking about the identity matrix, ones at the diagonal, and for all the other elements are 0. For all the other elements within the matrix, they have the value of 0 except for the diagonal, which is 1. Okay, it has the value of 1. So conditions: a square matrix A has an inverse only if A is non-singular. In other words, the determinant of A should be different than 0. If determinant of A is equal to 0, then the matrix is singular and non-invertible. It has no inverse. And this is why. The formula for 2 by 2 matrix: if A is equal to A, B, C, D, what would be the inverse matrix of A? A minus 1 is equal to 1 divided by determinant of A, which is AD minus BC, multiplied by A and D should be swapped. We should place D in place of A and vice versa. It becomes DA. As for BC, they don't change position, but they should be multiplied by a negative sign. We invert their signs. And since we are dividing by the determinant, this is why it is important to have AD minus BC different than 0. Because otherwise, if it's 0, you cannot divide by 0. This entire thing would blow up to infinity, and it's not defined among the real numbers. For an n by m matrix, A minus 1, or the inverse of A, is given by the adjacent of A divided by determinant of A. Now, that A, we already know what is that, how to evaluate it, and that it should be different than 0, so that A would be invertible. However, what is the adjacent of A? Adjacent of A is the transpose of the cofactor matrix. We will get to that later. Now, first of all, let's understand some key properties for invertible matrices. Let A and B be invertible matrices of the same size, and K, a scalar number, be different than 0. First of all, the inverse of a matrix that is already inverted, so inverse of an inverse, gives us back the original matrix. A minus 1 minus 1 gives us back the original matrix A. We are inverting the invert of a matrix, you get back the original one. Inverse of a product, so AB minus 1, the inverse of A multiplied by B, is equal or equivalent to the inverse of B multiplied by the inverse of A. And in order, which means that the inverse of B to the left and the inverse of A to the right. Inverse of a transpose, so the inverse of a transposed matrix, or AT minus 1, is equal to the transpose of the inverted matrix A. Inverse of a scalar multiple, which means when you multiply the matrix by K, a scalar number, and you invert it, it is equivalent to the inverse of the scalar times A minus 1. Okay? So notice something here. It is unique that here in this case, you need to invert the scalar itself. Identity matrix, I minus 1 is equal to I, so nothing changes. The inverse of the identity is equal to the identity itself. As an example, A equal 4726. Okay, at first, let's get the determinant to make sure it's not 0, so that we can confirm that A is invertible. So that of A is equal to 4 times 6 minus 2 times 7 equal 24 minus 14 equal 10. Different than 0, so it is invertible. Second, we swap 4 and 6, okay? Not 4 and 5, 4 and 6, by the way, it's a typo here. And you multiply 7 and 2 by minus, so 4 becomes 6 and 6 becomes 4. Then 2 and 7, we multiply them by a negative sign. Finally, we multiply that by 1 over the determinant of A, the inverse of the determinant. So a minus 1 is equal to 1 divided by 10 multiplied by 6 minus 7 minus 2, 4. This is the inverse matrix of A. Now, how to get the inverse matrix for a matrix having a size larger than 2 by 2? Okay, at first you have the Gauss-Jordan elimination method to find A minus by transforming A into the identity matrix using row operations while applying the same operations to I, the identity matrix. Okay, let's check how it works. When we're done, the right-hand side becomes A minus 1. Okay, so given an n by n invertible matrix A, so at first, you need to form the augmented matrix, or in other words, you place A next to the identity matrix of the same size. So let's say A is 3 by 3, 3 rows by 3 columns. So I next to it, separated by this line, would be 3 by 3. Okay, then we use row operations. So we swap, multiply, add between rows to transform the left block, A, into the identity matrix. And then the right block will then become A minus 1. Okay, so we need to change A, to use all of these operations so that A to the left becomes the identity matrix and I becomes A minus 1. Now, row operations, so swapping two rows, determinant changes sign, except we're not computing the determinant here, okay? So we multiply a row by a non-zero constant, we add, subtract multiple of one row to another row or from another row, okay? We will see how it plays out. So let's start with the first example. Okay, A equal to 1, 5, 3. We need to get the inverse matrix of A, or A minus 1. First step is forming the augmented matrix, where you place A to the left, then a separation line. After that, right next to it, to the right, the identity matrix having the same size of A, which is 1 by 1, okay, 1, 0, 0, 1. Second, which is step 2, make pivot in row 1 to equal, to become equal to 1 and divide R1 by 2. So, okay. Now, if we divide R1 by 2, you get 1, 2 divided by 2, so element by element. The entire row, we're dividing it by 2. Or in other words, you can write it as R1, so this is the operation. The first row is equal to this first row divided by 2, okay? So 2 divided by 2 is 1, 1 divided by 2, 0 0.5, 1 divided by 2, 0 0.5, 0 divided by 2, 0, okay? So this identity matrix to the left has started to shape up, to form now, okay? As for the second row, what we're going to do to the second row so that we can get, we need to get it to become 1. At first, we need to, for this value, for 5 to become 0, correct? That's the first thing. So, how we get there? We simply evaluate this operation. So, R2 is equal to R2. How do we eliminate 5? We multiply the first row by 5. So this element becomes minus 5. And we add them together so that this becomes rendered as 0. So R2, the second row, is equal to R2 minus 5 R1. Which is, you have in the second row 5, 3, 0, 1 minus 5 times this line, so minus 5 times 0 0.5, correct? I don't know how much. Then minus 5 times 0 0.5 again, this is 5, and minus 5 times 0. You add them up, you get 0, 0.5 minus 2.5, 1. After that, we make a pivot in row 2 equal to 1. So you multiply the second row, okay, R2 by 2. So how do we get that? Yeah, R2 is equal R2 multiplied by 2. So what we had before is 0, 0.5 minus 2.51. If we multiply by 2, 0 remains the same, but 0.5 becomes 1, correct? And of course, this will change. Minus 2.5 becomes minus 5, and here becomes 2. Let us look at it. Okay, so 0, 1 minus 5, 2. All what remains to be done is to remove the 0.5 here so that we can get the matrix, the identity matrix to the left. Okay, so how to get rid of 0.5? Okay, we simply do this following operation. R1 is equal to R1 minus 0.5 R2. Okay, so R1, the result or the new line R1, the new row R1 is equal to R1, the original values, minus 0.5 R2. So here you have 1, here 0.5 times 0, it is the same. Okay, here you have 0.5 minus 0.5 times 1, which is minus 0.5. Then you have 0.5 minus 0.5 times minus 5. Okay, times minus 5, correct? Then finally 0 times 0.5 times 2 doesn't matter. Okay, yeah, I'm sorry, R1 minus 5 times minus 0.5 times 2, which is minus 1. Now what we get is 1, 0, 3 minus 1, 0, 1, 5 minus 2. Notice something, this has become the identity. So the identity matrix has shifted from right to left, and what we end up with to the right is what is simply the inverse matrix A minus 1. And you can do the same thing using, you can use the same method for matrices larger than 2 by 2 size, 2 columns by 2 rows. Okay, so the left block is now I, and the right block is A minus 1. So this is the inverse matrix at the end. This is the overall solution. If you would like to take a picture for it, okay, to store it as a memory, a snapshot, but it is using the Gauss-Jordan method, because we have other methods to evaluate the inverse matrix. Now this is where we get back to finding the inverse of a matrix using the transpose of the cofac, which is the adjacent of A. This is what we've suspended before, and I mentioned that we're gonna get back to that method of resolving this problem. So let's say you have a matrix A, 1, 2, 3, 4, but I need to get the inverse of this matrix using cofac method. At first, we need to get the determinant of A, which is 1 times 4 minus 3 times 2. So A minus 1, and this is the solution, this is the formula, is equal to 1 divided by determinant of A, that of A, multiplied by the transpose of cofac of A. Now for 2 by 2 size, it won't be that difficult. Okay, so 1 divided by 4 minus 6 multiplied by, we simply swap 1 and 4. This is uniquely for 2 by 2 matrices. The cofac would become a little bit different for the 3 by 3 matrices. So we swap 4 and 1. As for 2 and 3, this side we multiplied by minus, so we end up with minus 2, 1. 3 divided by 2 minus 1 half. Okay, because we multiplied this 1 divided by that of A, which is 1 minus 2, by the entire matrix, element by element. Using the Jordan method, so you have 1, 2, 3, 4, 1, 0, 0, 1. At first, we need to get rid of 3 here on the second row. So this is done by R2 equal R2 minus 3R1. 3 minus 3, 0. 4 minus 3 times 2, which is minus 2. 0 minus 3 times 1 is minus 3. 1 minus 3 times 0, 1. Then, next to that, we need to get rid of this minus 2 here. So we divide this line by minus 2, so that we get, instead of minus 2 plus 1, R2 is equal to R2 divided by minus 2, which is 0, minus 2 divided by minus 2, which is 1, minus 3 divided by minus 2 is 3 over 2, and 1 divided by minus 2, 1 half. And finally, we remain with this element. We need to get rid of it. And this is how we do that. R1 is equal to R1 minus 2 R2. Okay, so 1 minus 2 times R2 times 0 is 1 minus 0, which is 1. Then 2 minus 2 times R2. So 2 minus 2 is 0. Then 1 minus 2 times 3 divided by 2. So 1 minus 3, which is minus 2, etc. And 1. So you end up with this inverse matrix, the same result we've obtained using the transpose of cofac. Again, it will be slightly different for 3 by 3 matrices, how we get the cofac, and we will get there. But whether using the Gauss-Jordan method or the classical method of transpose cofac, you will get the same result. Find the inverse matrix of 3 by 3, A equal 1, 2, 1, 0, 1, minus 1, 2, 3, 0. Again, the formula is A minus 1, or inverse of A, is equal to 1 divided by that A multiplied by the transpose of cofac A. Let's start with determinant of matrix A. So it is 1, 2, 1, 0, 1, minus 1, 2, 3, 0. And we replace the square brackets with these two line brackets, equal to 1 multiplied by 0 plus 3. After that, you have minus 2 multiplied by 0 minus 2 times minus 1, which is plus 2. So minus 2 times 0 plus 2. Then finally, 1 multiplied by plus, okay, plus minus plus. 1 multiplied by 0 times 3 minus 2 times 1, which gives us minus 3. The determinant, which is different than 0, so A is invertible. We can find an inverse for matrix A. Now, cofac of A. How to get the cofactorial? For the first element, you bar actually the intersecting row and column, first row and first column, and you find the determinant of this smaller matrix here, which is 1 times 0 minus 3 times minus 1, which is plus 3. So it is plus 3, hence you replace this plus 3. This is the first element of the cofactor. Then let us clear the slate again. So let us say that, and you go element by element. The second element here for 2, 0 minus 2 times minus 1, so plus 2. However, you have a negative sign. Don't forget. The second element here is 0 minus 2 times minus 1 plus 2. Okay, so this should be plus 2, I think. Yeah, it is 0 minus 2 times minus 1 plus 2. So let's check it. This is the cofac. It is minus 2. Yeah, why is that? Because it is multiplied by minus on the outside. Don't forget that. So again, we bar these two intersecting row and columns. The minus sign, don't forget it. 0 minus 2 times minus 1, which is plus 2. Then you have the minus on the outside, since you have an even column. So it gives us minus 2. Let us continue. What you have after that, this element 1 here, it is positive. You have a plus sign. We evaluate the determinant underneath the intersection of this row and this column, which is 0 times 3 minus 2 times 1 equal minus 2, multiplied by a plus sign, it remains minus 2, so this is minus 2. So on and so forth. I'm gonna, continue with some few examples. So in the middle, you have plus here. You go from left to right. So this is supposed to be plus. What we have here, you bar the column and row, and we get 1 times 0 minus 2 times 1, so it should be minus 2, and this is minus 2 in the middle. Then another element, plus, minus, plus, minus, plus, minus, plus. This should be plus here. The sign should be plus. So what would be the value at that location? 1 times 1 minus 0 times 2, which is 1. All right, with a plus sign, so it is plus 1, and this is plus 1. Let us find out another position, so to speak. Okay, so we have this one over here. Now let us find the sign. So you have plus, minus, plus, minus, plus, minus, plus. This is also plus. So what would be its value? We evaluate here. 2 times minus 1, minus 1. Yeah, forget about these signs here. These pertain to the external value. Plus, and you multiply it by 2 times minus 1, minus 1. So minus 2 minus 1, which is minus 3, and multiplied by a plus sign, so it is minus 3. Hence, you get the cofac of A. We need to get the transpose of the cofac, which is, we simply flip the columns into rows, respectively. So this column becomes a row. 3 is 3, minus 3. Then minus 2, 1. The second column becomes the second row. Then minus 2, 1. The third column becomes the third row, which is this one over here. So the inverse of A, the inverse matrix, is equal to 1 divided by determinant of A, which is 1 divided by determinant of A is minus 3. 1 divided by minus 3, or minus 1 over 3, multiplied by the transpose of cofac A, which is 3, minus 3, minus 2, 1, minus 2, 1, equal, if you want to expand it, or you can leave this value on the outside, to minus 1, 1, 2 third, minus 1 third, 2 third, minus 1 third, minus 1 third. Of course, you can pause the video and try to do the exercise yourself. Same example, the same exercise using the Gauss-Jordan method. So using the Gauss-Jordan method, A minus 1 is equal, you place both A and next to it the identity matrix of the same size, n times n, which is 3 by 3. So this is A, and this is the identity matrix corresponding to it. We need to transform the left side into identity matrix so that the right side would become the inverse matrix. How to do that? Okay, at first, 1 is okay here. We already have 1 and 1 here. We need to get rid of these side values so as to get zeros in all the places except the diagonal, which will only hold once. We start from the third row up. So you evaluate R3 minus 2 times R1. So this is what's happening. Basically, R3, which is this line, minus 2 R1. You have 2, 3, 0, etc. I don't care about the other values. And minus 2 R1, which means minus 2 times 1, minus 2. Then minus 2 times 2, minus 4. Minus 2 times 1, minus 2. And minus 2 times 1, minus 2. The remaining values are 0. Okay, you have 0. Here you have 0, 0, 1. So you add these two up, you get 0. 3 minus 4, which is minus 1. 0 minus 2. Okay, minus 2. Again, minus 2, 0, 1. And this is what becomes of row R3. 0 minus 1 minus 2 minus 2, 0, 1. Now, after that, I need to get rid of this value here to make it 0, so that we can start seeing the actual identity to the left. So how to get rid of this 0 over here? We simply add row 3 with row 2. So R3 is equal to R3 plus R2. So this is what we have. We have 0 minus 1, this is R3. 0, minus 1, minus 2, minus 2, 0, 1. And you have 0, 1, minus 1, 0, 1, 0. Let us add these two lines together. So this gives us 0, 1 minus 1, 0 also. Minus 1 is minus 3. Then you have minus 2. 0 plus 1 is equal to 1. And 0 plus 1 is equal to 1. And this is the result. Now, we triangularized the matrix to the left so far, but I need to get rid of 2, 1, minus 1 on the upper side of the diagonal, and I need this value to be 1. So let us continue. I need to make minus 3 here 1, correct? How to do that? We simply divide the third row by minus 3 altogether. Okay, just like a linear equation. When you multiply all of the equation by a value, it doesn't change the parameter. Like 3x plus 4y equals 0, you can multiply by 2. The entire equation doesn't change anything. Here, the same concept is at play because these 3 lines, 3 rows represent 3 equations. And you can mix them up together because they have the same parameters, the same unknowns from the first equation all the way to the last. So it's a system of linear equations. You can consider it as that. It goes by the same rules. So R3 is equal to R3 divided by minus 3. So this is R3 divided by minus 3. You have 0 divided by 3, 0 divided by 3, minus 3 divided by, divided by minus 3. So minus 3 divided by minus 3, minus 2 divided by minus 3, which is 2/3. Then 1 divided by minus 3, minus 1/3. 1 divided by minus 3, also minus 1/3. So what we get is, from left to right, 0, 0. Minus 3 divided by minus 3 is plus 1. And here you get 2/3, minus 1/3, minus 1/3. And you can see it clearly here. So far, we've gotten the upper triangular matrix. But it's not enough because we need to get rid of these two values to make them 0. How to actually do that? Let's get rid at first of this value here, which is minus 1, to render it 0. So we simply add the second row with the third row. R2 is equal to R2 plus R3. Let us see what happens. Second row plus third row. Let us add them together. So I won't rewrite them again. Actually, let me add them on top of each other. So this is R2, this is R3, second and third row. So 0 plus 0, 0, 1 plus 0, 1. By the way, R2 plus R3 is placed in R2 on the second position. Okay, so 0 plus 0, 0, 1 plus 0, 1, minus 1 plus 1, 0. Then 0 plus 2/3 is 2/3. 1 plus minus 1/3 is 2/3, 1 minus 1/3, and 0 plus minus 1/3 is minus 1/3. This is the second row, We still have this value that we need to get rid of, which is the 3 over here. We need to get rid of this value, so R1 is equal to R1 minus 3 R3. So again, R1 is equal to R1 minus 3 R3, correct? This is R1, so you have 1, 0, 3, 1 minus 2, 0, minus 3 times the third row. So this gives us 0, 0, minus 3. We're multiplying by 3 and minus 3 actually. Then 2/3 times minus 3, it is minus 2. Minus 3 times minus 1/3 is plus 1. Then minus 3 times minus 1/3 is plus 1 also. So you add them together and we get, and you need to place them at R1, I'm sorry. I got mixed up a little bit, I'm sorry. So it is R2, yeah. Okay, so R1 is equal to R1 minus 3 R3. R1 is equal to R1 minus 3 R3. Okay, which is correct, and we need to place it back into R1. So this results in 1, 0, 0, because 3 minus 3 is 0. Then minus 1, minus 2 plus 1 is minus 1, then plus 1. Let us check it out. Okay, so you get, minus 1 plus 1, correct. and 1, 0, 0. So this has become the identity matrix here, and this is the inverse matrix. So A minus 1 is equal to minus 1, minus 1, 1, 2 third, 2 third, minus 1 third, 2 third, minus 1 third, minus 1 third, the same exact value we've gotten using the other method of the cofact.